Hello everybody and welcome to the introductory lecture of our third project. In this lecture series, we will build a neural network which will automatically segment the left atrium in cardiac MRI images. As usual, let's talk about the background first. Segmenting an image is the process of assigning a specific class to all pixels or voxels in an image. In our case, this means that each voxel is either classified as not left atrium or left atrium. This segmentation of the atrium allows to exactly calculate its volume. Changes in atrial volume are associated with multiple cardiac disorders such as atrial fibrillation or mitral valve stenosis, which basically is a narrowing of the mitral valve orifice, blocking blood flow to the heart chambers. However, as you might already imagine, manual segmentation is an extremely tedious task, because the radiologist has to manually segment the left atrium in all slices where it is visible. Therefore, let's automate it. Alright, let's talk data. We can use the cardiac MRI dataset provided by the Medical Segmentation Decathlon. The Medical Segmentation Decathlon, or in short MSD, is a challenge consisting of 10 different medical segmentation tasks. Atrium segmentation is one of them. The corresponding dataset consists of 20 MRI scans of the heart with corresponding ground truth masks. In the two-dimensional setting, it adds up to 4,542 single slices. As usual, you can find the license and detailed instructions on how to obtain the dataset in the corresponding Jupyter notebook of this lecture. Now it's time to take a look at an example. This video shows one example of the dataset. You can beautifully see how at first the left ventricle joins in, followed by the left atrium, which is visualized by the red segmentation mask. Can you imagine why it looks like the patient is lying on his stomach? Please take a second to think about this. It's the RAS orientation of the scan. As the y-axis in the sagittal orientation moves from posterior to anterior or from back to front, the top rows of the image visualize the back of the patient. In contrast, the x-axis slices from inferior to superior or from bottom to top. Therefore, the left columns visualize the stomach and the right one the neck. Now, let us take a look at the necessary pre-processing steps. In general, there are two ways we could tackle this problem. The first possibility is to work in the three-dimensional setting by using 3D convolutions. However, using three-dimensional convolutions is extremely memory-hungry and computational expensive. Therefore, let's work in a two-dimensional setting by extracting the single slices. Our original image shape is 252 squared. However, as we are only interested in the cardiac regions, we could crop away some non-cardiac regions and the background by removing the first 32 rows or columns from all borders. Please note that you also have to crop the segmentation mask. Next, we perform a Z-normalization on a subject level. This means that we compute mean and standard deviation for each subject separately before Z-normalizing the corresponding scan. Subsequently, we standardize the normalized subject into the 0-1 range by performing min-max scaling. To evaluate the generalization ability of our model, we only use 16 patients as training data and the remaining 4 for validation purposes. After pre-processing our data, it's time to talk about the dataset. At first, our dataset needs to create a list of all two-dimensional slices. Next, given an index, it has to load the slice and corresponding label mask. After loading our data, we have to augment slice and mask identically. Last but not least, we need to return the augmented slice and mask. We use scaling, heavy rotation and elastic transformations for augmentation. Elastic transformations augment an image by moving the pixels locally around using a displacement field. Before talking about the training routine, let's discuss the model. We will manually implement one of the most famous segmentation models in this lecture called UNet. The UNet was proposed by Ronnenberger et al. At MICHI 2015. It consists of an encoder-decoder architecture with skip connections. The encoder has the task of reducing the feature maps by using normal convolutions and max pooling layers. In contrast, the decoder has to reconstruct the segmentation mask based on the original image and the features by using upsampling layers and also normal convolutions. Last but not least, the use of skip connections allows an information flow directly from the encoder to the decoder. This drastically reduces the problem of vanishing gradients. The next slide shows a possible representation of this model. In the blue part, the encoder, we can see how by using convolutions together with max pooling layers, the image is progressively processed and boiled down. In the red decoder, the smaller feature maps are gradually brought back to the original image size by using upsampling layers, also combined with convolutions. Last but not least, by using the shortcuts or skip connections, we can directly forward our information or feature maps from the encoder to the decoder. The details will be much clearer once we program the model. Alright, now it's time to talk about the training. We will train our model by using the Atom optimizer with an initial learning rate of 1e-4 together with the currently most used loss for segmentation tasks called dice loss. The dice loss is defined as 1 minus 2 times the sum of the intersection between the predictions y hat and the labels y divided by the sum of our predictions y hat plus the sum of our labels y. In code it looks as follows. As we are working in a binary setting, we can simply compute the intersection in the counter by calculating the sum of the element-wise product between prediction and label. The denominator is simply calculated by adding the sum of the predictions to the sum of the masks. Additionally, as both prediction and mask might be 0, we add a really small number to the denominator, as an example 1e-8, to make sure we never divide by 0. We can now compute the dice score by calculating 1 minus 2 times the counter divided by the denominator. Typically, the sigmoid activation function is applied to the raw predictions when using a dice loss. With a threshold of 0.5, this results in all pixels with a value greater than 0.5 being assigned to the Atrium class and all pixels with a value less than or equal to 0.5 being assigned to the non-Atrium class. Last but not least, we train our model for 75 epochs. Alright, it's again coding time. Thanks and happy learning!